Okay, so it's 6:05, and yeah, so we can start. So hello everyone, myself Gaurav Kumar, I'm coordinator of IBEC. For the fourth talk of IBEC APSD talk series, today we have with us Dr. Surajit Mondal. Welcome, sir. So before we start with the talk, I would like to give a short introduction of the speaker. So he is currently a postdoc fellow at the National Center for Radio Astrophysics (NCRA), Tata Institute of Fundamental Research (TIFR). He also got his PhD from the same NCRA TIFR and received his master's degree in physics from IIT Kanpur. His research work revolves around using solar data to understand solar dynamics. He has also worked on different technical aspects of extracting maximum scientific information from the observed data. And he will be giving the talk today titled The Dynamic Sun. And we will be having the Q&A session at the end of the talk. And you can keep posting your questions in the chat box. We will take note of those questions. Also, if there is urgent question which you need to ask in between the slides, you can raise your hand and unmute yourself. Okay, so now we can start.
Hello everyone. Uh, so the title of today's talk is the Dynamic Sun. Before beginning, I would like to thank the organizers for inviting me to give this talk. I have prepared my presentation in a way such that I will go over the very basic stuff and slowly build my way towards the slightly more advanced topics. So if you feel that this is a repetition, please bear with me, and hopefully by the end of this talk you would have found something interesting. With that, let's begin. So when I was a small child, I was taught how to draw the sun. It was basically it looked like this. Okay, so this was the globe of sun, and these are the different light rays emanating from it. And actually for a very long time, this was the idea of what was with people about how the sun looked like. It was unchanging in time. And when telescopes were used to observe the sun, something entirely different was seen. So what was found were, in the images taken by the telescopes of the sun, they found that there were these spots in the image. It was not immediately appreciated that these spots are actually spots on the sun until the discovery by Galileo Galilei. He was the first to identify that sunspots are actually spots on the sun. And the fact that these sunspots were changing from day to day was evidence that the sun was dynamic. Hence, this was the first identification of solar dynamics. Now, what are sunspots? Sunspots are regions where the observed solar intensity in the visible light is much fainter than its surroundings. So it appears dark. Here, this is an image taken from the Solar Dynamics Observatory, which is an instrument launched by the NASA. Okay, so you see that the sunspots are much darker than its surroundings. Now it is darker because the temperature of the plasma which is inside these sunspots is much lower than the surrounding medium. Now, the area of these sunspots can be very large. Even it can be much larger than the size of Earth. Now that can be seen from this image. See, this is the approximate size of Earth. And you see the sunspot is larger than the Earth itself. However, there are also smaller sunspots as well. And you can find some small sunspots here and there. Okay. Now these sunspots are actually the locations where the magnetic field is very strong. The magnetic field inside sunspots are of the order of few kilogauss. Now, as I mentioned earlier, that these sunspots change from day to day. If you count the number of sunspots every day for several years and plot it, how the number of sunspots is changing as a function of time, you see this beautiful diagram. There is some sort of a periodicity of 11 years in the number of these sunspots. Apart from this, there are some key interesting things to note here. See, in a span of about 50 years, there was not even a single sunspot on the solar disk, or very few. Okay. Remember, the periodicity is 11 years. So it was very surprising that for 50 years, there was very hardly any sunspot on the solar disk. Another thing to note is that the maximum number of sunspots observed in these cycles is also not same for every such cycle. So it is not that just the number of sunspots that is changing and is showing this 11-year cycle. If you see, the area occupied by these sunspots also show a similar variation and shows a similar periodicity of 11 years. It is shown in this diagram. Now, this is another beautiful property of these sunspots. So the sun can be divided into these latitudes in a very similar manner as which can be done in Earth. These spots are generally seen in a latitudinal belt of plus minus 30 degrees. So now towards the beginning of this 11-year cycle, see, when this sunspot number is very low, the most of these sunspots are seen at plus minus 30 degrees. Now, as the number of sunspots are increasing, see, these sunspots move towards the equator. And at the peak of the solar cycle, by peak I mean the time at which the number of sunspots is the maximum, at those times the sunspots are often seen even in the equator. Now, so it makes this sort of a diagram that, like, as if the sunspots are slowly moving from the northern and southern latitudes towards the equator. This diagram is known as the butterfly diagram, and it shows how the location of sunspots are changing from year to year. So till now, I have talked about 3 different types of dynamics regarding the sunspots. First, the number of sunspots show a 11-year periodicity in general. Second, area of sunspots also show an 11-year periodicity. Third, also have seen the butterfly diagram, which shows how the spots are moving from the northern and southern latitudes towards the equator. Now, these spots are observed in the visible light. Using this visible light, we can only observe the photosphere in general. The photosphere is the lowest layer of the solar atmosphere. However, there are other layers of the solar atmosphere as well. So there is the photosphere, then there is the chromosphere, then there is the solar corona. Now, all these layers emit in the visible wavelength. But since the photospheric light is so bright, it is not possible to observe the optical light from these layers in presence of this photospheric light. So the only way to observe these or the only way to observe these layers using visible light is to block the photospheric light. Nature gives us the opportunity to observe these layers in the optical band during solar eclipses. So during solar eclipse, the moon blocks the photospheric light, and then we can see the solar corona and the chromosphere. You might have seen some of the beautiful images of the solar corona taken during solar eclipses. I will show one of them today in my talk. However, the eclipses are very rare, and it generally cannot be observed routinely using the corona cannot be observed in a routine manner if we are to rely solely on these eclipses. However, there is another part of the electromagnetic spectrum which can be used to routinely observe the sun from the earth. That is the radio wavelengths. So how does the sun look like in the radio bands? Before going to that, I would like to point out some key differences between the radio observations of the sun and the optical observations of the sun. So this is the solar flux density as observed from the sun in the optical and the radio bands. So in the optical, the sun more or less behaves like that of a black body with temperature of the order of 5800 Kelvin. Of course, there are some multiple absorption lines which I'm ignoring for now. But see, in the radio band, the flux is much higher than that expected from a 6000 Kelvin black body. In fact, if you convert these fluxes to temperature, the quiet sun will lie on a black body whose temperature is 1 million Kelvin. An active sun, it can go exceed 10 to the power 8 Kelvin as well. Now this says that there is something very different happening in the sun which can only be observed from the ground in the radio band. That's the first thing to understand, that the optical and the radio wavelengths are showing us two different pictures of the sun. Next is the radio sun dynamic. I told you earlier that the optical sun is definitely dynamic. Now is the radio sun dynamic. Here, what is shown in the y-axis is the frequency of observation. The time is increasing along this direction. Please ignore these white dashed lines for now. So here, see, there is this bright structure here. The more red the color is, the brighter is the sun in that point in this graph. So see, at let us say 150 megahertz, there was nothing at this time. Suddenly we see that the solar flux density has increased. Then after some time, we don't see anything. We also see that this structure shows a drift towards lower frequencies with increase in time. So this shows that the radio sun is also dynamic. Now, let's see how the radio sun actually looks like. This is the radio sun on 2 different days. The black dashed line shows here the optical disk of the sun. The optical disk, I mean the sun which you will see in the optical band. Hello? Hello?
Yes, sir, you can carry on. That was a glitch, I guess.
Okay. So, two things are evident from this figure. First of all, while the optical sun has a clear geometric shape in general, the radio sun does not have any clear geometric shape. Secondly, the radio sun is much larger than that of the optical disk. Now, one might ask, so what is this structure? It looks very weird and it is not completely absent in this image. Actually, how the radio sun looks like depends on what is happening on the sun. Now, let me go in slight more detail on what is this structure here, which was completely absent in this image. This is the radio counterpart of something which is called coronal mass ejection. So let's talk briefly about what is a coronal mass ejection. Okay. So I mentioned earlier that the solar corona can be observed only if we block the photospheric light. And nature does that for us during solar eclipses. But scientists want to study the solar corona routinely, and eclipses are very, very rare. So an instrument by the name of coronagraph has been devised. So it produces artificial solar eclipses. You see this white circle here. So these are the two white circles that shows the optical disk of the sun. The radius of these circles are actually same if you actually get the angular length scales. It is just that it is slightly farther out. So in this is the occulting disk, which means the light.
Sorry to interrupt, sir.
Yeah.
Are you using pointer?
Yes.
We cannot see the pointer.
You cannot see the pointer. Okay. Wait, let me try to share my full screen. Hopefully that will. Yeah. So can you see now?
Yes, it's visible now.
So I was mentioning that this white circle here and here shows the optical disk of the sun. So that is the photospheric circle. Now, using these occulting disks, we can block the photospheric light. Actually, we don't stop there. We block all light till some given radius. So, for example, the occulting disk here is blocking all optical light till a radius of 2.25 solar radius. After that, we can see the faint optical light from the corona. Okay. Now, these coronal mass ejections are very nicely seen using these instruments called coronagraphs. So as you can see, there is this big blob of plasma. Now these big blobs of plasma often get ejected from the sun into space. These are highly magnetized. And these are called coronal mass ejections. This was first discovered in 1973 by Art Touche. Now, I showed you some examples of the dynamics on the sun. But today, I will focus on the coronal dynamics, means how the solar corona is changing as a function of time. Now, what is the source of these dynamics? The coronal dynamics is entirely governed by the magnetic field. But how does magnetic field lead to this dynamics? So for that, let me give you some introduction about this. So this is the sun observed using the iron line. Okay, there are these sunspots which can be seen here. Now, if you try to extract the line of sight magnetic field, you see that at the location of these spots, there are oppositely directed field lines. The white and the black regions show the opposite direction of the field line. Now, if you zoom into this location, and after some image processing and combining data from other instruments, you can make this beautiful diagram here. So these are the two sunspots which are seen here. The blue and the yellow shows the magnetic field direction. The blue and yellow are oppositely directed to each other. Now these white lines which you can see here are the coronal loops. So these coronal loops actually trace the magnetic field lines. So in some sense, you can imagine that these are the magnetic field lines which are emanating from these two coronal holes. It is evident that the magnetic field geometry here is quite complicated. You cannot describe it by a simple model. For example, the dipole model or quadrupolar model. Now, this complex magnetic field geometry in the corona can also be seen from eclipse observations. Here, I have shown an image taken during solar eclipse of August 21, 2017. You see here there are these open field lines. Here there are some cusp-like structure here. Here there are more open field lines. So it is a quite complex magnetic field geometry. Now, a phenomena called magnetic reconnection can happen in this complex magnetic field geometry. So what are magnetic reconnections? So imagine you have two oppositely directed field lines, very similar to that which we find here. Here we see this white and black, which are two oppositely directed magnetic field lines. Imagine there is some plasma flow which is pushing these oppositely directed field lines towards each other. Now, in this cartoon, as you see, that these two field lines have been given a new shape. So they have been slightly deformed. Now, as these two field lines come close to each other, a strong current sheet, which has large current, is produced in between these two field lines. Additionally, since the plasma is moving in just because of mass conservation, plasma should also flow out of here. So the plasma, let us see, is moving with velocity v in, and it is moving out with the velocity of v out. At this point, where they are the closest, a phenomena called magnetic reconnection happens. Due to this magnetic reconnection, the magnetic field topology here changes. So see here, the field line was directed along this, and this was along this. After reconnection, the field geometry has completely changed. It has taken a curved shape here and a curved shape here. And these field lines and the plasma along with it gets ejected out in both directions. So magnetic field reconnection is a process by which the magnetic field topology can get changed. Now I will show you a small video which can explain this in a slightly more better detail. So you will see that these are two oppositely directed magnetic field lines. The reconnection will happen at this juncture, and you also see the newly produced field line will move up along this direction. Additionally, during the process of this reconnection, I mentioned that strong current sheet is produced. So there are strong electric fields in system. Those electric fields accelerate charged particles to very high velocities. These accelerated particles will move along the magnetic field lines. With the introduction, let me play this video.
Angled magnetic field lines to explosively snap and realign, shooting out particles and energy.
So I hope, so you have seen that there was this bright light here which is produced, that was the sign that a reconnection has happened. After that, you saw that there is this white line, field line, which was moving up. That is the new field line which is moving out. Okay, it is similar to what I have shown here. Additionally, you also saw there are this purple charge particles which were accelerated due to this reconnection process, and they have moved along the magnetic field lines. I will again play the video for you so that you can watch it more closely.
Angled magnetic field lines to explosively snap and realign, shooting up particles and energy.
Okay. Now, this reconnection process dumps a lot of heat into the corona. This makes the corona locally very hot, and it becomes so hot that it emits in hard and soft X-rays. You see here, this blue and red lines are the X-ray fluxes at different wavelengths. So see that during such flares which are produced due to these strong reconnections, the X-ray flux has increased more than 3 orders of magnitude. It was about 10 to the power minus 7 here, and it suddenly increased almost close to 10 to the power minus 3 here. So in a very small span of time, the flux has increased by at least 1,000 times. So these are known as X-ray flares. Now, but you also saw that particles are also accelerated during this reconnection process. Now, is there any role of these particles in the coronal dynamics? To tell you that answer, let me go back to this image which I had shown earlier. So this was how the solar flux in the radio band varies as a function of time and frequency. So, as I mentioned earlier, this structure, you will see that as time progresses, it is moving towards lower and lower frequencies. So this is the drifting structure I'm talking about. As time is progressing, the frequency of emission is moving towards lower and lower frequencies. Now, as we explained now, this emission is caused because of these accelerated particles. Now, to explain that, I will explain something called the bump on tail instability. So, the corona is a million Kelvin plasma. Okay, so the distribution function is that of a Maxwellian distribution. Now, suddenly you have these accelerated particles which has been introduced into the system. So that means it will produce a bump in that distribution. Why there will be a bump? Because number of particles is expected at that high velocity is larger than that expected from a Maxwellian distribution. And these accelerated particles, why are they present? Because they have been accelerated by the magnetic reconnection. And this is the energy in the plasma wave levels. Now, this is not the condition of the plasma. The plasma will try to go back into the Maxwellian condition. The only way to do that is to transfer energy from these particles, the accelerated particles, to the plasma. So, how does it happen? So, it happens in this manner. So, these are the times. So, the different colors show the distribution function and the wave energy at multiple times. So, let's, for example, this brown shows at time t is equal to 100. Let's ignore the units of the times here. And 0 is the time, the initial conditions. So, you see, slowly, as the particle in this bump is losing energy, the energy contained in the waves are increasing. Now, till when this will happen? It will happen till this condition is satisfied. That the gradient of the distribution function is greater than 0. Till that condition, this transfer of energy from the particles to the waves will happen. And these plasma waves, through some other interactions, emit in the electromagnetic band, in the radio frequencies. The frequency of the emission is proportional to the square root of the local plasma density. The higher the density is, higher is the frequency of the radio emission. Now with this, we'll try to understand the drift which we saw earlier. What was the drift? It was as time progresses, the frequency of emission was moving to lower and lower frequencies. Imagine that this is the sun. I know this does not look like a circle, but this is just cartoon. The density decreases as we move away from the sun. Imagine at this location, the reconnection has happened and particles have been accelerated at this location. I mentioned that the observed emission, the observed radio emission, is proportional to the square root of the density. So let us, for time being, say that this is the emission at this frequency and at this time. So I forgot to mention, time increases along this axis and frequency increases along this axis. So as we go up along this axis, the frequency is actually decreasing. The next instant, the particles are somewhere here. Are somewhere here. Now the density has decreased now. So the radio emission will be at a lower frequency. So we move up. As time progresses, the emission is observed at lower frequencies. Now let's proceed in time further. It has went further up. So the frequency will decrease more. So this shows why we see this particular type of drift, that as time progresses, the frequency of the observed emission decreases. Now, I have talked about these magnetic reconnections. I also talked about that these magnetic reconnections can heat the corona so much that strong X-ray flares can happen. However, these big flares are relatively smaller in number. It is believed that small-scale reconnections are happening throughout the corona. And the hypothesis is that these reconnections are behind the corona, by which the corona maintains its very hot temperature. Now, how hot is the corona? The corona is a temperature of 10 to the power 6 Kelvin. It is 1,000 times hotter than the photosphere. Now, how do we know that the corona is hot? Now, I will talk about some history here. Initially, in the 19th century, people observed a spectral line which was not known but the source of the spectral line from the corona. Hence, they named it coronium because it was only observed from the solar corona. It was first detected by this person in 1868 at the Madras Observatory in India. However, due to bureaucratic red tape, the publication happened much later, and now the discovery is credited to C.A. Young. Okay? Now we know that this coronium line was actually the emission line of iron 14. So that is iron 13 plus. Now iron has a very large atomic number. You need a really lot of energy to generate iron 14 plus. So unless the temperature is very high, you cannot have iron 14. That is how we know that the corona is very hot. When it is so hot, you can always observe the corona in extreme ultraviolet bands. In fact, now we routinely observe the solar corona using optical and the UV bands. We also use other wavelengths, but for here I am only showing the optical bands and UV bands. So UV is the extreme ultraviolet, and we need satellites to observe the corona in those wavelengths. This is an image taken from the Solar Dynamics Observatory, which is a collage of how the sun looks like at different bands. See here, there's interesting temperatures here. This is how the sun looks like at 131 angstrom. This line comes from temperature is 10 to the power 7 Kelvin. So even in such a high temperature, we can find plasma in the corona. It is very hot. Now, I have given you some introduction about what we knew about the solar corona and about the coronal dynamics. We'll talk about what are the key research questions today. So one is something called the space weather, and second is the coronal heating problem. There are of course many more, but I will not have the time to discuss them today. So I mentioned earlier that during coronal mass ejections, plasma is ejected out. You saw here that the plasma has been ejected out from the corona. You can also see something here. So this big CME has erupted from the sun, and these CMEs have actually a very high momentum because of their huge mass and velocity, and they can often hit Earth. So this is the CME which is moving towards Earth. This is the Earth, and this is the magnetopause. Now, if the CME has sufficient momentum, it can push the magnetopause towards the Earth. If the magnetopause gets pushed sufficiently, then the artificial satellites might come in contact with the CME. Now that might destroy the satellites in a significant manner. Additionally, due to these CMEs, which also have magnetic field, magnetic reconnection can happen. So if the direction of magnetic field of the Earth and that of the CME are oppositely directed, then it will induce magnetic reconnections. These magnetic reconnections accelerate particles. I mentioned earlier. These particles can also penetrate this magnetopause and affect the satellites. Can also affect our GPS communications as well. That is why it's important to know when the CME will affect Earth. Now, nowadays, we can predict with relative certainty when big flares will happen. And big flares generally lead to big CMEs. So here is an example where some flare probabilities have been calculated. So the different colors show what is the probability of a flare of some strength. So we can do that routinely, and it is more or less accurate. But if you try to say, okay, the CME has happened, tell me how long will it take for it to reach Earth? Now, data for that was collected in this paper. Okay, these are several models here. So the time difference is in hours, and they're everywhere. Can even be off by 60 hours, is more than 2 days. That means we are still not in a position to accurately say when the CME will arrive on Earth. However, I mentioned earlier that the extent to which the Earth will get affected by a CME also depends on the magnetic field. If the magnetic field directions are opposite to each other, of that of the CME and that of the Earth, then reconnection can happen, which will cause severe damage to the satellites. However, the vector magnetic field of CME can only be measured now in a routine manner using in situ techniques. This gives us about an hour of warning to take any precautionary measure to save the satellites and other things. But we really want to measure the vector magnetic field of CME in a remote manner. Now, the radio observations can be very helpful to do this. It is done using the Faraday rotation measurements. So what is Faraday rotation? Imagine this is a magnetized medium. Now, when linearly polarized light passes through this magnetized medium, the plane of polarization changes. By measuring this difference between these two angles, and if we know the density of this medium, can get some idea about the vector magnetic field of this medium. Now, how do we apply it to measure the magnetic field of CME? So imagine this is extragalactic source, okay, which emits light in linear polarization. So when we observe this source through the CME, we can detect the change of its plane of polarization. By measuring this change, we can actually estimate the vector magnetic field of the CME. Now, I will briefly talk about a very interesting development about coronal heating. This development came from data was taken by Solar Orbiter. You probably have heard of the Solar Orbiter. It is an instrument which has been launched very recently, and it will go outside the ecliptic plane. The ecliptic plane is the plane in which the Earth is orbiting around the Sun. Now, it will image the Sun from very closely, and due to this, and also with advanced instruments, it could detect these phenomena called campfires. So campfires are very small flares. They're tiny brightenings in the corona. If you try to look at this very carefully, there are this very small enhancements in intensity in front of these arrows. These are thought to be very key to understanding the coronal heating problem. So I do not have much time to go into these in more detail. We'll stop after giving a summary of this. So I showed you today that the sun is very dynamic. I hope you have been convinced of this. And the deeper we look into it, the more complex it looks. But still, a far away from understanding even the closest star to us. Imagine just how dynamic our universe is. Thank you. And I will take questions now.